Static analysis tools are a mandatory security layer, scanning source code for vulnerabilities before deployment. However, these scans routinely generate a volume of alerts that exceeds what human teams can feasibly process. This high volume forces engineering teams into a specific triage protocol. They manually review the highest severity alerts, while leaving a vast pool of warnings entirely unreviewed. These unreviewed alerts represent unknown risk. In many large-scale codebases, real, exploitable vulnerabilities remain hidden within this unexamined data. The cost matrix for code adjudication is asymmetrical. A false positive costs an analyst time, but a false negative results in shipping an exploitable vulnerability. Because human attention cannot scale to the bloat of traditional static analysis, engineering teams have been forced to accept systemic security risks as a baseline reality. Researchers from Carnegie Mellon University, William Klieber, David Svoboda, Lori Flynn, and Ruben Martins, investigated whether large language models could close this gap. Their goal was to autonomously adjudicate these static analysis alerts. Their research demonstrates that naive, single-shot LLM queries lack the reliability required for high-assurance code. To solve this, they developed a structured pipeline called LASAA, LLMs for adjudication of static analysis alerts. On novel code bases, the LASAA pipeline achieves 98% recall in identifying bugs and over 94% specificity in dismissing false alarms. This performance is reached by forcing the LLM to output detailed reasoning chains that the system can algorithmically double-check, moving beyond simple true or false flags. Reliable AI code analysis requires wrapping LLM inference within a software engineering architecture designed to detect and mitigate inevitable model errors. Simple classification models often try to force a binary true or false label onto an alert. In real-world software, however, vulnerabilities often cascade. To provide precise feedback, the LASAA pipeline utilizes a three-way classification matrix: true, false, and dependent. Consider FormAI Alert 068671. The analyzer flags a signed integer overflow on line 56. However, line 56 uses a variable from a calculation on line 54. If line 56 overflows, it means line 54 already overflowed. The system classifies line 56 as dependent, identifying line 54 as the root cause requiring the developer's attention. Categorizing these dependencies allows the system to point developers toward the logical root of a vulnerability rather than a downstream symptom. Because LLM sampling is non-deterministic, a single inference run is too unreliable for security infrastructure. To counter this, LASAA implements a consistency check. Each alert is processed through 10 independent inference trials. To confirm or clear an alert, a strict threshold, typically 80%, of these trials must return the exact same verdict. When the trials fail to reach that 80% agreement, the system defaults to a verdict of uncertain. To maintain safety, uncertain alerts are treated as potential positives and routed to a human analyst for review. While this check prevents false negatives, it creates a new bottleneck by generating a high volume of uncertain alerts for manual review. A common method for resolving LLM disagreement is universal self-consistency, where the system simply takes a majority vote. In complex code analysis, a majority vote is risky. A logical oversight shared by the majority of runs can easily override the correct nuanced logic found in a minority run. LASAA addresses this with LLM Reasoning Evaluation, or LRE. The system bundles the discordant reasoning from the 10 trials and routes them into a new LLM node acting as a judge. In Alert 364317, the majority argued dependent, assuming a positive size parameter, but a minority noted a negative size creates a massive unsigned integer, returning a null pointer. LRE forces the LLM to evaluate the competing logic. It recognizes the decisive factor in the minority trace, the negative integer, and corrects the final verdict. This process shows that while an LLM may overlook a decisive factor during generation, it can successfully identify that same factor when tasked with weighing competing reasoning traces. To ensure a true positive verdict is grounded in reality, the system requires a method of physical verification. LASAA uses a dynamic trigger test, where the LLM must synthesize an executable C driver program designed to manifest the flaw at runtime. This driver is compiled with address sanitizer and undefined behavior sanitizer to catch memory errors and undefined behavior. Faster, more urgent tone. The program runs under GDB with a breakpoint at the flagged line. The test succeeds only if it produces a detectable fault exactly where the LLM claimed the bug existed. A separate validity check ensures the driver didn't cheat by violating standard function preconditions to manufacture the fault. A successful trigger test provides execution-based proof that the vulnerability is genuine. If models train on public datasets like Juliet, high accuracy might be a result of memorization rather than actual reasoning. To test this, researchers ran a file name reconstruction probe on sanitized Juliet code. The Model 04 Mini reconstructed the exact functional variant 68% of the time. Because it recovers test case identities from sanitized snippets, its Juliet benchmark performance appears driven by template recognition. Consequently, the team based their generalization claims on FormAI, a dataset of LLM-generated code, and their own unpublished manual adjudications. Validating AI code analysis requires moving past memorized benchmarks and utilizing novel, synthesized datasets paired with physical execution tests. When tested on the novel FormAI dataset, mid-tier reasoning models hit 99% recall and over 94% specificity using LRE and consistency checks. These results indicate that the reliability of AI in security depends more on system architecture than on the underlying model's initial guess. Consistency checks provide the necessary statistical guardrails, while reasoning evaluation resolves complex logical disputes by weighing competing evidence. Architecting systems that force an AI to rigorously cross-examine its own logic creates a level of reliability that single-shot prompts cannot reach.